Hey, what's up, guys? Chung here again. And so today, let's take a look at another LeetCode hard problem here, number 818, race car. So you have a car, and the car at position 0, and speed, the initial speed is 1. And at each step, you can do two things. Either accelerate. If you do accelerate, the position, the next position or the current position of your car will be moving to the current speed. Plot basically your position will be moving to the next position by adding the current speed. And after doing that, your speed will become twice as before. So that's what the acceleration A will do. And another option is that you can do a R here. So if you do R, basically you just simply stop. First, your position will stop at the current step. And if your speed is positive, then you get a speed equals to -1. Basically, you turn around, right? Otherwise, your speed equals to 1. Basically, it's turn around on each direction. If you are facing to right, and then it will be turning around back to 1, to the left with the speed 1. And if you're same thing, if your current state is heading toward the left, and you do a R again, you'll be heading to the right side again with still with the speed 1. Okay, and it asks you, it gives you a target and asks you what's the minimum, the shortest sequence of instructions to get there. So today I'm gonna talk about two solutions here. The first one is a BFS, which is the kind of a little bit more intuitive, and the second one is the DP, dynamic programming. So let's take a look at the first solution, the BFS search. And so I think the thinking process to come to the BFS search is the when you find this length of shortest sequence, basically the shortest path, right, to get to the target. You know, when you guys see find a problem with anything that has the shortest something, you know, it's not 100% sure, but for the BFS search, right, one of the purpose of BFS search is find the shortest path, right? From shortest path from the from start to the end, right? There are a bunch of other or shortest result problem, like you can also do a so for a binary search problem, it may also ask you about shortest answer. But for the binary problem, to be able to solve, we're using a binary problem. All the candidates there have to be sorted, right? But in this case, it's not sorted because you can either go to the right or even go to the left. And another way of doing the length of the shortest thing is by using the DP, of course, right? And the third one will be the BFS, right? Because with BFS, it's easier to find if you do a BFS, if you build a graph, and if you build a graph and you have a BF, and you need to find with the graph, and you do a BFS search, it's easier to find the length, the shortest length. So, and the graph for this is like basically you need to know the edges from one node to all its neighbors, right? And for this problem, it's always two edges from the current from the current state or current node to its neighbor. It's either accelerate or reverse, right? And for each node, we need to to store its state, right? Or a unique key for that. In this case, it's going to be the position plus the speed, right? That can uniquely identify identify the each node. It's just similar as the DP problem. For DP problem in this case, we're also gonna need the 2D DP because we need both the position and the speed to annotate the current state. Same thing for the BFI search. So let's take a look at the BFI search. So for the BFI search, it's like just regular BFI search. At each state, we'll try to branch out by either A or R. Of course, we're gonna need to check if this state had been visited before, right? And another some improvements for BFI search is the when this like the speed or the position reaches certain point, we don't want to continue. So our stop our stop point will be if the speed if the speed the absolute value of a speed if the absolute value of the new speed of the speed or new speed is greater than the two times of the target, and same thing for absolute position, right? It's also greater than two target. So either the speed or the position has exceeded more than two times of target, we just stop. Why? There's not like very strict proof for this stop point, but it kind of makes sense, right? Because let's say the speed is it's way over on either side, right? So there's no point of continue doing the continuous keep going, right? Because the speed is too fast, right? So if you keep going on that direction, there's no point because we're already too far away from the target, right? And same thing for the position, right? So the speed, if the speed is too fast, it means that we there's no point of keep going at the current speed. We should just stop, right? And same for the position here, right? So if the position is like it's way too over. It's way too over on one side, right? As in we also need to stop. Mm. Okay, cool. So let's try to code this thing. So other than that, it's just like very standard BFI search template. Basically, we're gonna have a scene set, right? And then at the beginning, right, the first state is gonna be the at position 0 with speed 1, right? And then we're gonna have a queue here, right? So since it's gonna be the collections.dq, right? So mm, mm, yeah, and the steps, right? Steps equals to 0 while q, right? While q, and then we do a mm, range length. This is how I do a BFI search, by the way. There's some other ways you can do it, but I just prefer using a for loop here. So the position and the speed, right? Pop left, right? So and the new position will be we're gonna calculate the new position first, right? The new position is the position plus speed, right? And if the new positions is equal to the target, right? We simply return the steps plus 1, okay? So after this, the new speed will become the new speed will be uh, 2 times of the old speed. Okay, so now the acceleration. So now the first is keep the first case will be A, right? So like I said, when should we keep accelerating, right? Do we need to keep accelerating? Basically, we check if the position, right? If the current position ABS of the speed, okay, the new speed, it's smaller than the 2 times target, right? And the ABS of the new speed, the new position, the new position is also within the 2 times of target. Then we can continue. Otherwise, like I said, if either one of them is like has exceeded 2 times of the target, there's no point of continue. And of course, right? So and the new position and the new speed has not been seen before, right? If that's the case, we just add this new state to the queue, append new position and the new speed. Okay, and don't forget to add this out to the to there, right? Okay, so that's the A, right? And for the B, for the R here, right? So for R, there is no like there's no like this kind of check because with R, there basically the state, the position didn't change, and the position stays with the current position, and speed will become either zero, either become -1 or 1, right? So we don't need to check this because there will never be over the boundaries in this case. So we simply just get the new speed. Uh, I'll get new speed 2, right? Equals to if it's -1, if the speed is greater than 0, right? Else 1, right? So same thing. So here we just need to check if the old position, since it's not moving, and the new speed 2 is not in scene. That's all we need to check, right? If that's the case, then we just do this. But remember, it's going to be the old position, the new speed 2, and here as well. 2 parentheses here, right? So yeah, I think that's that. So we can either do a return or not, but because it doesn't really matter because we will definitely find our answers here. We'll return here, so it will never reach here. So yeah, so basically that's the very it's a very basic BFS search for the accel. Oh, sorry, let's try to run it first. Oh my God. Uh, 3. Okay. Uh, target. Okay, and position and not in scene and add. Hmm. Uh, I think I know what happened here. So I forgot to increase the steps here in the end. Yeah, right. So every time the BFS, the most important step for BFS maybe increase the steps. All right, let's try to run it. Yeah. So yeah, it passed. All right. So yeah, so for the BFS, it's to a recap about thinking process. So you need it. You're asked to get the shortest length or shortest step from one state to another, right? And then on each of the state you have several edges you can choose. In this case, either A or R, and then you can start thinking about, can I solve this problem by the BFS search, right? And what are the conditions to add a new edge, right? And what's the stopping point, right? Okay, so cool. That's basically the BFS search. Now let's go to the DP solution here. So the DP solution is more difficult to come up with the state transition function. Okay, so okay, let's say you have a hmm, I'll just draw it here. Let's say you have this one line here, and assuming we have all the A, right? And you know what? I'll open this whiteboard here. Yeah, it's easier for me to draw. Okay. Okay. So let's say you have A. You have K A's, right? And basically for the DP, you have to think about how many to get to the target, right? Uh, to get to the target, like how many ways we can get to the target. Let's say we have a target here, T, right? So if you do let's say you have a K minus 1A. So basically, if the T is between the K minus 1 step and the K step, right? This is the K minus 1, and this is the K. Let's say T is somewhere in between, right? So when I say K or K minus 1, I means how many continuous acceleration we have been made here, okay? And so that the value is going to be so what's the value of this? So the value is like the position, yeah. So the position, uh, so the position for this place is it's like 2 to the 2 to the K minus 1, K minus 1, right? K minus 1, minus 1, yeah, 2 to the K minus 1 to the power of K minus 1, and this position is the 2 to the K minus 1, right? Because we keep accelerating every time the speed doubled up, right? So that's the position we can get at the 2 to the K minus 1 plus 1, right? You can this is like the math formula here, right? So because you do a 1 plus 2 plus 4 plus 8, right? So in the end, you can conclude with to this like 2 to the k minus 1, and this is the 2 to the power of k minus 1, right? So let's assume the t is somewhere in between, right? And what are the ways we can get to the t, right? So first we can go to the k 2k minus 1, which is that we have already passed the t here, right? So if okay, one so the first condition is, let's say we already reached the k, which is uh, already past the t. Then what do? We need to turn around, right? So and when we turn around, so when we turn around, okay, so the distance, right? The distance between the 2k minus 1 minus t, right? That's the distance from here to here. Okay, so what I'm saying is that so from k here, we're gonna turn around. We're gonna heading back to the t, right? And then you guys maybe have already realized that for this t here, for to turning back from here, this once we have already turned back, the speed will start with 1 and it will head to the t, right? It's this is the sub problem, right? Basically, this part from this point to t here, so there we're gonna have like a dp sub problem, right? The it's the 2 time of k minus 1 minus t, right? So that's the problem, right? Because the problem is that so dpi we are defining like from speed 1 or from speed 0, right? What's the minimum step we can get to this position, right? So by turning around at this position k here, we can transform this part to another dp sub problem, because we can easily prove that this sub problem is a smaller sub problem, because we have already been calculated this value before, because we are calculating from the left to right, and when we reach the k, we have already passed this dp problem already, right? So okay, so and that's the sub dp problem, and how many steps we need to take to get to this dp state, right? So first we have k steps, right? That's the k, and we do one reverse, right? So when we do a reverse, we need to plus 1 here. So this is the reverse here. Basically, when we reach k here, we turn back. We turn back, and then the rest will be converted to a sub dp problem here, right? From 1 to the target, but in the opposite direction. Okay, so that's the first. So that's the first scenario, which is kind of easy to understand. And the second scenario is more complicated. Basically, and so the first one is one after we pass the t. Second one is the it's right before we reach t, which is the 2 to the k minus 1 minus 1. Basically, we stop from here. Once we stop from here, we'll try to turn around. We try to turn around here, and then right, we try to turn around, and then it's we're gonna reach a certain point here, right? So let's say the point here is it's like the J steps here, right? J step, J ace. So basically, once we turn around from K here, we do J's acceleration, and then we turn around back again. Do another R here. Okay, so and from this point over, from here to the t, basically from here to the t again. So from this point to the t again, so this will be also become another sub problem, right? And but in order to get this position here, we have to try all the possible j's here, because let's say for example we can accelerate once and then we turn around, and we can accelerate twice. We have 2a's, 3a's, 5a's until the k minus 1a's, right? Because I think the maximum we can go back is basically before hitting zero, right? So basically, if you're or even if you traverse turn around too far away, even like bypass our original starting point, that you will not definitely not get a better answer. So basically, that's why at each point here, at each of the the 2 to the k minus 1 point here, we only try the possible a's up to the k minus 1 times. And then once we have that j step fixed, then we'll do another turn here. We'll do another turn to make it reverse it back towards t, and then the rest will become another sub problem. So then what's the dp transition function, state transition function for this scenario, right? So first we have a k minus 1 step to get to this position, right? So that's the first step, right? Second is the first is the k minus 1 step to get here, and then we do a turn here, right? That's going to be a plus 1, right? We do a plus 1, and then we have a j step to get to j, right? With plus j. See. Uh, k plus 1. Okay. 1, 2. Okay, let's see. Yeah, so right. So and we have another, we turn around once here to get to the j's acceleration, and then we do another turn around. Okay, right. So that's the steps we need to take before converting this problem, before converting the rest into another DP problem, right? So what's the DP problem here? So now the DP, we need to do the DP here. So DP should be from the current state, the distance between here and the T here, right? So what's the difference? The distance, sorry, the distance. It's the as you guys can see, right? So the distance is the T minus this part, right? Minus from the start to right before we do a J's like turn, right? Then this place this distance equals to to what? To the position here minus the reverse distance, right? So it's gonna be that the position of here is like 2 to the k minus 1, right? And minus 2 I'm talking about the distance. I don't do a -1 because if you do a -1 here, I also need to do a -1 here. So I'll just use the relatively the distance because we want to get the difference, right? So the 2k minus 1 minus 2 to the j, right? So basically, so this 2 to the power of k minus 1 minus 2 to the power of j will give me the difference from the beginning to here, right? And then I do a t minus this position. It will give me the distance between the current position and the t, which will be another sub problem, right? And so the j here is going to be we're going to do a minimum, right? Minimum of this one. So the j is like starting from 0 to the k minus 1, right? Sorry, k minus 1. That's the range of j because we will not go over the 0 here. Okay, cool. So that's basically mm, the two scenarios to get to the t here. Someone may argue that how can you prove this this solution, right? These scenarios can give you the optimal result, right? I mean, you can also argue that, like let's say why do you have to stop at the case here, right? Why can't you stop at anywhere like before k, before 2 to the k minus 1, right? Can you stop somewhere here right in between, right? Then that may give you like a better option, right? Um, yes, that's possible, but the problem is that if you stop somewhere between the t and the 2k minus 1, we don't have a sub problem to to I mean to use, right? So basically, and if you stop at here, right? If you stop here, but since we are also like calculating all the possible ways, we stop before the k minus 1, right? So that can somehow guarantee us we can get a best we can get the correct answer out of these two scenarios here. And yeah, so I think you guys can just assume, yeah, this will give you the best answer out of these two possible conditions, right? So, and here's like one. This is R, right? This is also R here. Yeah, I don't know how can I prove this solutions to be correct, but I'm just thinking of this like the only the only ways I can get close to the answers. Otherwise, if you don't use this K point, right, you try to use somewhere in between here, and you don't know the step basically, right? So with this K steps here, with this like a K 2 to the K minus 1, we know how many steps we need to take. We know exactly how many steps we need to take to get to the current state, which is the K. And here's the K minus 1, right? If you try to use anything in between here, the steps is not fixed, right? So basically we cannot do like a state transition function here. So we have to basically it's not cannot be solved by a DB problem. That's why I so we have to rely on these two like conditions here, right? Oh, and one of the edge cases, if the t if t equals to this, if the t equals to the 2 to the k minus 1, then the answer will be k itself, right? That's the best scenario, right? So the t's we just keep accelerating, and only with k steps. We never need to reverse, Cool. Okay, so let's try to code these things up. So, and okay, so with the DP, we're gonna create like a DP array here, right? Since we're getting the minimum, we're gonna initialize everything to be the maximum, and the size will be the target minus one, the target plus one. Okay, and then we start from the first position, right? In range, uh, target plus one. Okay, so we start from here. Okay, so we start from here, and now we have a target, right? It's a target. We need to know what we need to know the range of the steps, those how many accelerations, how many A's we need to take to get to this target, right? So in Python, there's like let's do a target here. In Python, there's like functions called bit length, which it will give you the bit length to get to the current number. That's exactly the numbers we need. Basically, we need to get like the 2 to the time of k minus 1, right? And less than k less than 2 to the k, right? So we need to get the target here, basically to the 2 to the k, right? So in Python, we can simply use a bit length to get to this like the k number very easily, right? And then we have a special case here. So if the t equals to 2 to the time of k minus 1, right? And then we simply do a dp t equals to k, right? Well, actually, we can simply return. Not return. Sorry, we cannot return it. We have to do continue because the best answer for the current target here. So we don't have to try the other possible ways. So else, right? Else basically basically the DPI would equals to what? Will equals to the minimum, right, of DPI. That's every time so the first step is going to be that we pass target, we pass T and turn back, right? Like I said, in this case, and so first we will need to k steps to reach that step, the point that passed T, right? And then we do another we use another step to do a turn around, right? And then the rest will become uh, so the current position of k is 2 to the k, right? That's the positions minus 1, right? So that's the current position minus 1 and minus t, right? So the position is 2 to the power of k minus 1. That's the current position. And then we do a minus the t. T is the current target, right? So that's the range, basically, right? From that point and when we turn back to the t. So that's the first scenario. Second scenario is we stop at 2 to the power of k minus 1 and zigzag. Okay, yeah, so this thing's like a zigzag, right? Zigzag back. Okay, right? And so for that, we have to do I'm going to use J in the range of basically this J means how many accelerations will zig back, right? And then we'll turn around back, right? We'll do basically two reverse. So the range will be a k minus 1, and up until to k minus 1. So the dpi will becomes to the dpi to the so first we'll take k minus 1 step to get to that first stop point, right? And then we do a reverse, right? And then we take j step, we took j accelerations, and then we do another reverse to come back, right? And the rest will be the dp, like the t minus, right? Like the difference, right? The difference is the okay, so that's the 2 to the power of k minus 1 minus 2 to the power of j, right? Yeah. And in the end, we simply return the dp target, right? So that's the last one. Okay, let's try to run it. Sorry, dpt. Okay. Yeah, as you guys can see, this DP problem is much faster than the previous one because the oh sorry, okay, let me finish the recap here. So the code is kind of short, but the thinking process is long and hard, especially for these two scenarios, and especially for this one. Basically, when you do a zigzag, right, you have like k minus 1's options to choose your turning point, right? But when you pass the t here, you have we're only giving you one options. So right after you pass this like this t here, you only have one options, but to turn back. Okay, but here we have k options, k minus 1 options to go back with j's acceleration and then turn back again. Hmm. Okay, so how about the time complexity here and space complexity? So first, for the BFS search, right? So for the BFS search, as you can see, every time we have two options here, and we have a basically we have a zero, we have a target, we have targets like the node here, right? Or the possible target nodes here. No, sorry, not possible target nodes. So every time we have a new position or we have a new state, we'll be having like basically we're gonna make them into two times that many nodes, right? So basically the time complexity for this BFS search is gonna be somewhere for the n sorry, it's the 2 to the power of n. The n is somewhere close to the target, right? But since we have this kind of like a boundary check here, the the time complexity is much smaller than this, but for in normal case, right? So this the time complexity is gonna be 2 to the power of n because each time, right, we have a new node. We're gonna spawn two different branches, right? And the space complexity is also the same, 2 to the time of n because that's the numbers we were gonna have in this queue here. Yeah. So, okay, so that's that. And how about this DP problem, right? So for DP problem, we have a target here, right? So the first one is the let's see, this is n, right? Okay, I'm gonna use n here. So the first one is n, and how about the second one here? So within the n loop here, right? So we have another for loop here, right? But the for loop here is not it's not n, right? Because we're only looping through by the power of 2, right? So we're looping through the k, we're not looping through the target here, right? So the inner loop will be like the log n here, right? Because we only looping through the power of 2. So the time complexity for this dp is the n log 2. How about the space? Space, we have a space complexity, we have an n here, right? That's the dp here. And hmm, do we have another space here? No, I think that's it. Yeah, we just use this deep the on space here, dp. Mm. Yeah, so the space is just on here. Hmm, let me see. Oh, and before finishing up this videos here, uh, so for DP problem, the reason we can define like a DP at most to target or target plus one is because, even though we're gonna have like I said, even though we're gonna pass the target somewhere on the K here. So like I said, we have a target here, right? And there's like K minus one, 2 to the K minus one, and then 2 to the K, right? So even though we're gonna pass the uh, the T to and then advance to the 2 to the K, but we can approve that 2 to the K minus 1 minus T is always smaller than the target. Okay, that's why for the DP here we only need up to this length of DP because this one is smaller than the previously target. That's why we can reuse the previously calculated DP result to help us to get to the current state. That's basically that's the as that's the essence, right, of the DP. Or I think essence, it's not essence. I think sorry about my pronunciation. It's the essence of the DP. Uh, we use the previously calculated result to get to the current state, right? Uh, yeah, okay, I think that's pretty much it is for this problem. I know it's a hard problem, I think for you guys, if you guys find this DP solution is really hard to understand during an interview, I believe this BFS solution should be enough. Yeah, because it's um, it's more intuitive, right? You just start with one state and then you try to find the shortest path to another state, and you just need to be careful about so you cannot branching out indefinitely, right? You have to stop somewhere, right? And then for a DP, it's a little bit tricky and it's hard to prove its correctness, right? And cool. I think that's it for this problem. Thank you so much for watching the videos, guys, and stay tuned. I'll be seeing you guys soon. Bye bye.